Yeah, but it doesn't seem to take the S of the next energy level. If it takes its own S, it's going to grab its own B's.
When you're talking about general energy levels, it goes 3s, 3p, and then 4s.
Yes, it does. But the 4S gets left alone when hybridization.
Like, because there was like a question, and they were out of order, like all these places in the
Forecast or
Yeah,
until
that is. It's fine to do it like that. The order's not as important as the fact that all the electrons are accounted for in their thing.
Yeah, but you have to maximize the
All right.
derivative. Okay.
Now I have a summary. If this doesn't make any sense to you, you still may need to be asked, hey, what is the hybridization of central line? The hybridization is just another way of expressing the coordination number. It's taking the coordination number that we learned about. We looked at this coordination number of 3. And describing what's happening with the orbitals. So this, I have one more, and then I just have a summary. This slide gives us a definition. Okay, a sigma bond is where you have a direct overlap of hybrid orbitals, and a pi bond is where you have a connection of non-hybridized orbitals. Write that down now, and then I'll show you a picture, a model of what that looks like.
What do you mean by the last?
This? It says the non-hybridized P, which is that one right there, is the one that makes the second bond. That's the pi bond.
No, I just what?
Between.
Yeah, it's BW. BCBW. Because
I'm not using texting language, Artin.
no, it's BW. No, it's BW.
No, it's not.
Yes, it is.
B/T is between.
No.
No, it's
B/W is
pretty sure. It's actually.
You guys are misguided. I feel bad for you.
It's
like the
more.
whole class
It is
is-
B/W.
Yeah, that's why that's why I asked.
Oh, that's what you weren't sure about?
Or AP texters,
Hey,
we
BT is
know.
what?
Yeah, you're advanced
Oh my
texters. I need to, I guess.
It's okay, but you're the only one that got that.
Oh my God.
Like, I hate it when people just use or anything. I just type out everything. And our tag is bad at about the use. Yeah, they're over.
I can't believe it. He's like, every time I said BT, this kid is like, oh.
Oh, wow.
I know.
Nobody said anything in my first 2 hours of this class, so you're the wacky ones, just so you know.
We're the ones
Wait, did you actually change it?
It's more, it's like, they're probably
I'm sorry. I'm sorry I said.
yeah, it's first and second hour.
I feel bad.
Okay, are we good with that?
Yeah.
So notice, whatever your coordination number is, that's how many orbitals the atom needs to hybridize to make possible to make those sigma bonds. And so the hybridization, when only 2 are needed, 2 orbitals, that means you take the S and 1 of the P's, it would be just called sp hybridization. If 3 orbitals are needed, you need the S and 2 of the P's, that's sp2, and so on like that. When you get to 5 and 6, it's sp3d, and 6 would be sp3d2. So that's just describing how many orbitals and which ones in the valence shell have hybridized.
Mr. Moore,
Yes?
just to be an idiot, I wanted to ask you for the iridium 9 hybridization thingy. Is that like a D6 then? Or no, D5? SP3 D5?
I have to look back to that iridium. Was that in the paper?
Yeah.
Or from his lecture?
Well, it wasn't in either, so I just wanted to know if they kind of...
When you say 9, is that a positive 9 oxidation state?
Yeah. Oh, so it doesn't
Same
make
thing.
it doesn't make covalent bonds, does it?
No, it's a metal.
Okay, that's what I was... Wait, but then metals can still make covalent
Yes,
bonds.
they can.
Wait, what?
You recorded yourself as an idiot.
It's got a positive charge, though, a positive oxidation state. Probably make it.
Okay.
Maybe not. Maybe not.
Okay.
Positive 9. This is so dumb.
That's awesome.
Too many.
Positive.
Yes? What's the shape of that complex?
You said just to be two.
Brood?
They just like us to
F's? Maybe for iridium, that's what it does.
I didn't realize I was recording myself.
I guess it's
It
possible.
sounds like one of those AC.
Yeah. Those are big obnoxious structures. That's not true. Artea? Yeah. Yeah. But sometimes you won't even need all 4 of the S's and the P's. Like in this case, you only needed 1 S and 1 P. And then you're going to have 2 non-hybridized. That probably means that there's 2 pi bonds in that, on that sector.
What if it's like something like, orbital 180? You say SP3 and the D and then SP3.
You'll never go above 6. You'll never go above 6.
What if, like, say SP3D?
We would. You can't go above 6.
Oh.
Actually, you can, but we're not going to. There is, it's possible to have coordination for a 7. That would be SP3.
But you can't go really
I don't know of it. Fine, Artea, 100.
Then you'd have to go to the 4th dimension.
This is what, yeah, 4th dimension. Let's talk physics. And
What was
then
happening when you were gone for a whole second? They would not stop
And
talking.
then there's always
They would not stop
I
talking.
want you to at least see what a sigma bond and what a pi bond potentially look like. A sigma bond is this area in green. A sigma bond happens when a hybridized orbital of one atom overlaps the hybridized orbital of another atom. And they share 2 electrons in this green region. That's what a sigma bond looks like. A pi bond is very different. Pi bond happens, notice this blue is one non-hybridized p orbital. And this is a non-hybridized p orbital, that's what it says, p orbital. Electrons can be shared across those p's with this bridge kind of thing that they make. This little river-looking thing, that's a bridge. And the electrons are being shared kind of outside the region in between the 2 atoms. That's a pi bond. This pi bond has 2 parts. Pi bonds always have 2 parts. One above, one below the sigma bond. They always do. You never have a pi bond with just 1 part to it. It's always above and below. That's why the pi bond is pointing in 2 different things. It's not 2 pi bonds, it's 1 pi bond. It's got 2 parts to it. A sigma bond is stronger. It's a stronger attraction than a pi bond. Pi bond's broken easily because they're kind of exposed to things that can come along. We did this in the organic chapter.
So that green orbital is the SP orbital, hybridized orbital.
No, that would be one of the SP hybridized orbitals.
One.
And then there's going to be this carbon. One of its orbitals is bonding to this carbon, and then the other orbital is bonding to something else, H or another C or something.
Mhm.
Okay.
So that's an SP2 hybridized. Or no, that's SP or hybridized.
This is just a model for what a sigma bond looks like, what a pi bond looks like. We don't know what else the carbons are doing, so it may be SP2 and it may be SP. That's just SP. But it's not SP3 because you wouldn't have any pi bonds if it's SP3.
Uh-huh.
Anna?
I have 2 questions, but they're really fast. So for that, would that be just 1 pi bond? So it's just
This is 1 pi bond.
Okay.
Yeah.
And
This
then,
makes up a double bond.
Yeah.
Sigma and pi.
And then also, so pi bonds are shorter, right?
The double bond is shorter than a single bond. Everybody, I want you to hear that. In fact, that was what I was just going to say next, is that I want you to know that a single bond is made up of a sigma bond. It's strong. A double bond, though, is stronger. I told you that the sigma is stronger than the pi, but them working together is stronger than just a single bond. So a triple bond it has the 2 atoms very close together because 3 sets of electrons are being shared. So when you have the 2 pi bonds and the sigma, that is drawing those 2 atoms that are bonded very close together. When you have a double bond, that's not as close as a triple, but still close, and then a single bond is farthest apart. One of the homework exercises I know is that, hey, rank these in order of the bond length. Well, you have to do the Lewis structure and see how many bonds are between the atoms, and that's going to indicate what's the longest. the single bond is going to be the longest bond. Artea? It is. They're kind of, yeah. They're being shared. You've got electrons in here somewhere and in here somewhere. Yet they're being shared across those two. Yeah. Weird. They're kind of being shared in a non-defined place. That's up there though. Yeah. Approximately.
Why can't they just have like lone pair and like that's
A lone pair would be occupying a hybridized
They don't have to share. They have the lone.
These two carbons, this carbon has one electron and this carbon has one electron. Those electrons want to be, they're more stable when they're paired up. So if this electron jumped over here to make a lone pair, then this carbon's not going to have 8 electrons around it. It's only going to have 6. No good. So it's got to have 8. That's why they share. Yeah. All right, my friends. It's 12:01, so we're now out of time. And well, we can do an example here. I was really hoping that we could start. I don't know how we're getting so behind. I guess it's all the questions that are asked, but are all the people complaining about BTs and BWs? Maybe that's what slowed us down so much. Yes. But tomorrow we're going to have intermolecular attractions and formal charge. We've got 2 topics to take on tonight. We have to get through it. So don't ask me any questions.